Tens of millions of dollars and sort of that level of
yeah.
Okay, I'll start with the note well now, and then I'll introduce you, Stephen, and then we can start. We'll start with you screen sharing, but okay. Hi, everybody. Through this seminar that will be given by Stephen, I'll introduce him after I do the note well to allow people to join in online and fix their IT issues. So I'm going to spend the next 2 or so minutes just going through the note well as usual per IETF policies.
Don't think anyone here is actually wearing a red do not photograph lanyard, but if you are.
It does say online at the end. But yes. And as this is the last slide, I just want to again highlight what's in the middle. The IETF is about research, not standards development. So we do want to foster research collaborations, etc. So we highly encourage asking Stephen questions, and he can then clarify when introducing himself whether he wants to accept questions during the talk or to wait afterwards, and so on. Okay, thanks for this. I will stop this, and I would like to now hand over to Stephen, who's joined us. And Stephen is Stephen Diademo. Is it Diademo or?
Yeah, Diademo.
Okay. Is a research scientist at Cisco and the quantum research group of Alireza Shabani. He did his Bachelor's of Computer Science at the University of Toronto and Master's of Mathematics at the Technical University of Munich in Germany. He continued with his PhD in electrical engineering at the TU Munich in the group of Yanis Notzel, where he worked on developing simulations and protocols for quantum networks and developing architectures for distributed quantum computers. His current work involves architectures for future quantum networks and application development and simulations of quantum networks. And with that, I would like to hand over to Stephen. Stephen, can you just clarify when you would like questions? Thanks.
Question, yeah. So firstly, thank you for the introduction and for hosting me here. For the questions, you can ask me during the presentation, but if I think it's better, if something's coming up, maybe I'll postpone answering. So we could try with that first, so during the presentation. All right, so yep, so thanks again for the introduction and having me. So this talk is about this concept we've been thinking about a little bit about packet switching in quantum networks and how we think it could lead to a quantum internet. So this is the work that we have released in May, and this is the collaboration with Bing Chi, Glenn Miller, Romana Compella, and Alireza Shabani. So we have already been introduced, but I just quickly show a picture of my face in the sunlight. So I'm Stephen. I work at Cisco. I've been there for about 1 year now, a little under a year, 10 months or so. I've been working on quantum network designs, a little bit of information theory. In my past, distributed quantum computing and simulation is my main focuses. So this presentation, I'm going to firstly introduce what is a quantum network. I know probably we all know this, but I just want to make sure that we're all on the same page with the definitions I use. I want to explain what does a quantum network do briefly. Then what I'll do is I want to look at the existing architectures of a quantum network. So this one, as I said, is about packet switching in quantum networks, but what else is there? Then we can explore this packet switch quantum network idea in terms of future vision, and then explore the challenges we will face in trying to build such a network. Then we look at some applications that could work on this type of network in the near term, and then I go over a bit of an outlook. So to start, we talk about what's a quantum network. So a quantum network is something that is a type of network that connects quantum capable devices. And that doesn't always mean that every node in the network is quantum capable, but just some network nodes are quantum capable. That could mean, a classical computer sending classical information to a quantum computer, maybe receiving some quantum information back. Could also mean that you're connecting quantum computers together. It could mean that you're transmitting quantum states using some kind of attenuated laser and detecting it somewhere else. So these channels that these quantum networks use are generally over free space or over fiber optics. I guess fiber optics is more popular, but you can also do quantum communication through satellites. And the transport medium is generally photons, so you encode quantum information into a photon, and that's usually the type of quantum system that's used for transmitting quantum information. Although somewhat less popular models are based on ions and other things like that, but usually when I talk about sending quantum information, I mean encoding that into a photon. And the stack, like how does a quantum network work? It's generally so far been proposed like an OZ layer model. So you have application layer, transport layer, network layer, link layer, physical layer. These kind of ideas have been kind of integrated into quantum networks, and they work. All those layers might be a little different than what we're used to in the classical sense, but that structure of breaking out what's the responsibility of each layer is kind of been developed a little bit, and that looks like an OZ model. So that's what I believe is a quantum network. And a kind of a picture of what a quantum network looks like is, in the different scales of the network, you can have a kind of local area where you're in a data center, kind of like we heard just a little bit ago, where you're connecting quantum computers together, and you're not going out of the room. All the traffic is isolated to a small area. You could also have kind of a wide area network where you're connecting to a city together. So you have some users who are maybe they're doing QKD over a metropolitan area. And then you can also have wide area where you're connecting multiple quantum networks together. And when you kind of get into that regime, you need some device called a quantum repeater, which you use because you can't copy quantum states, and therefore you can't, in general, amplify quantum states. And you need to use this quantum repeater technology in order to go to arbitrary distances in the wide area sense. Alternatively, you could also use satellites to go a little bit further. I mean, maybe not arbitrary distance, depends on the application, depends on the configuration, but satellites can be used to extend the range of quantum networks, and you can kind of mix and match the two systems together to scale in distance and to scale in other aspects. So yeah, these connections are probably fiber optics. It could be free space, and potentially even like radio frequencies. So what do we want to use quantum networks for? So first, I think the most popular use case at the moment is for quantum key distribution. This is the nearest term application that we're seeing a lot of field deployments of quantum key distribution networks. And it's mainly because it's a little bit easier to do than other quantum network applications. We have the technology to implement these things already, so this is a main thing. And the quantum key distribution, as we probably all know, it's the ability to transmit secret keys, but with the knowledge that no one else knows what that secret key is, except for me, the person sending the secret key, and the receiver I intend to have that secret key. Another big application is in blind quantum computing. So this means you are performing quantum computing over a network, but the person who has the quantum computer doesn't necessarily know what algorithm you're running on their quantum computer. So you might be sending them quantum states, they perform quantum algorithm on those states, they send them back, and they have no clue what algorithm was run on those qubits. Other aspects are distributed quantum computing, so you can connect quantum computers together over a quantum network to perform larger scale quantum algorithms. And the final one that I'm mentioning here is networked quantum sensors. So you can connect a bunch of sensors together that transport quantum states between each other. And in principle, you can potentially measure time, magnetic fields, gravity, and other phenomena with a higher sensitivity than we can do with just classical technology. So what we are looking at Cisco a little bit right now is less on the application layer. We're kind of more focused on the lower parts of the network. We are thinking about the networking aspects. So this is more where I'm focused on, is the protocols that we use to transport quantum states, simulating quantum networks, the control of a network, the security aspects of a quantum network. And then we also think about the hardware aspects of a quantum network. So can we develop better optical routers and switches? What's inside a quantum repeater? What's the way to design those to work with the technology we have? And also quantum memory technology. So as you mentioned, we're kind of a young group. We were about 1 year old. I mean, sorry, I started 1 year ago, but the group started maybe 2 years ago. So these things are kind of like in the vision. We're not selling these things right now, but this is a long-term vision. What do we want to focus on? Or these topics, and of course we work towards that. So now I will look at the designs for quantum networks that are, I would say, the most popular and the most far along in terms of how much work has been done around those designs. And the first one I look at is this quantum key distribution networks. The quantum key distribution network is a network of nodes that are performing quantum key distribution with each other. So if you look in this picture, you see these nodes numbered 1 through 48 or so, or 0 to 47 or 46, I don't know. It's but each node, what their goal is only to do quantum key distribution with any other party in the network. So it could be 1 in 7, could be 1 in 20, it could be 2 in 20. So any pair in this network should be able to perform quantum key distribution. And this picture is actually kind of a depiction of what has been deployed in this work I cite here. And this quantum network is a quantum network, but I call this a quantum key distribution network because it has only one purpose, and that is to do QKD. And therefore I say it's not general purpose. So you can't run, for example, some other quantum application because it's not designed to do that. Moreover, this quantum network is designed to work kind of side by side with the classical network. So in some cases, these fibers are deployed simply for this quantum network. They're not using the shared systems that exist in the city for doing classical internet. And this quantum network, as I said, has been deployed, and it can be working. It works with available optical technology. One aspect to note is that these trusted repeaters you see here are kind of a compromise made in order to scale the quantum network up to bigger distances. For example, maybe with 18 kilometers fiber, and I don't know, maybe this is again 5 kilometers or less, maybe the attenuation is so high that node 8 and node 2 can't communicate or can't have a positive key rate because there's just too much loss in the system. So to get over those kind of things, you have these trusted repeaters who perform QKD intermediately. And there's a kind of a compromise because we don't have quantum repeater technology. So that's how QKD networks overcome scaling issues in general. I mean, not in general, but in this particular setting, is using trusted repeaters, a trusted relay. The next design to discuss is this kind of entanglement-based quantum networks, I call them. And what I mean by that is it's a network who uses entanglement to transport quantum information. The way it does that is for two arbitrary nodes in the network, they firstly need to establish entanglement between the two pairs. And once that entanglement is established, then they use the protocol quantum teleportation to transport quantum states from point A to point B using classical information. So in the most simple case, teleportation uses 2 classical bits, and you consume your entanglement. Entanglement is no longer available once it's consumed. Convert that into 2 bits of classical information. Now the sender doesn't send the qubit, but rather sends 2 bits of classical information to the destination. And then the protocol does a little bit more. And in theory, the qubit that was at location A is now at location B over using only classical communication and entanglement resources. So the way that the routing is done commonly is done. Yeah, okay, sorry, I'm not talking about routing yet, but I want to talk about using a classical interface. Sorry, Wojtek, I hope I'm not misrepresenting this paper, by the way, so feel free to interrupt me. So this is it's working side by side with the classical internet. So again, this kind of concept of putting the quantum network beside the classical internet is something that's commonly seen, where the vision we're about to propose, we kind of want to use all the same fibers. Yeah, so this last point I want to make is that this type of quantum network is general purpose, meaning any quantum state can be sent in this fashion, but it's a bit of a technologically challenging because you need to be able to robustly distribute entanglement, and you might need to store the quantum entanglement too. And this might lead to slow rates. For example, if you're just doing BB84 prepare and measure, maybe you're better off doing direct transmission because it's more efficient. So there's kind of a compromise to make there. It depends on the application. So these are the two types of networks I think are most commonly seen. What I believe from these two designs are that they seem to be on a road that will not easily lead to scalability. They're using types of switching mechanisms that are a bit, things we saw in the past that we had to get rid of, as a circuit switching model or static switching models, which don't really allow for, many users in some cases. But maybe it can, maybe it can't. We don't know. We have to study that. But in general, we swapped away from circuit switching, but now we're bringing circuit switching back, and we might not want to do that. And maybe they're not supporting all applications of quantum networks. Okay, that's a thing. That's a big problem to solve in this current technology era. But if we start thinking about how will the entanglement-based network support prepare and measure QKD, and vice versa, how can QKD network support entanglement-based network, and kind of thinking about supporting many applications now instead of building one type of network up very deeply and then finding out, wait, we can't actually run another application that we care about in the future. So you maybe want to start thinking about that. So the design vision for quantum networks that we're seeing is that future quantum networks should integrate with the classical internet and should already start being designed accordingly to coexist. So what do I mean? So we want these kind of three pillars of quantum networks, is that they should have universality, meaning they should serve all quantum network applications in a more or less fair way. They should have transparency, meaning they should integrate with classical technology as much as possible. So we don't want to put more fibers beside the fibers that exist. We don't want to have independent hardware all the time. Of course, that's a big demand to ask, but we should think about that. Can we do anything? Should we start thinking about that now? And the scalability. So we should have protocols that allow for scalability. We should transport quantum states in a scalable way. We shouldn't, rely on circuit switch models all the time, because maybe that's going to prevent us from scaling. So maybe this is a bit of a harsher slide, but these are the shortcomings we find. So we find that these types of quantum network designs are application specific. So QKD networks that have been deployed are designed to do QKD only. Of course, there's an exception where we've seen some QKD networks that coexist or a classical fiber, and showing some examples, but this is kind of a new thing that we're seeing. Haven't seen like full-scale deployments. Entanglement-based networks are general purpose, but maybe not well suited for prepare and measure based protocols like BB84 and maybe others, because we have to rely on robust entanglement distribution and storage. They're not so user scalable, so that means we're relying on switching methods that we've seen in the past don't scale that well for many users in particular network settings. And we don't want to rely on always entanglement-based networks, because we were thinking about like connection-oriented all the time. We want to move away from that a little bit. And then integrability. So this means how well do these types of designs integrate with what exists in the classical regime? Do they integrate with the classical internet? Can we do anything with the current switches that work for classical internet? can we do anything with that technology, and has it been proposed in those designs? We see that maybe it's lacking there, and we want to kind of integrate the network stacks to be a bit more integrated. So we want to think about the same routing approaches, maybe same types of protocols in some of the layers, so that we don't have to reinvent things that might come up. We can start thinking about, can we do some task using methods that exist? We want to integrate that with the classical, with existing, developments instead of reinventing. Okay, so that leads us to our packet switch quantum network. And so as a first step in this direction, this work that we've done is kind of investigate what would it take to do packet switching for quantum networks. And we want to investigate the main challenges for this type of network. We don't think that this is something that's going to come out in a year or two, because this is definitely some kind of long-term vision that will have many challenges to overcome. And in the near term, of course, we're going to have to make compromises, just like the other architectures have done. So we're not saying that this is the solution to everything, but it's a potential solution for overcoming things that we saw in the past that we want to kind of think about now instead of waiting. So yeah, just to emphasize a long-term vision and not something we think is going to be solved in anytime soon. I mean, maybe by anytime soon, but maybe in 10 years, but not tomorrow. So yeah, I think I've been using these words already, but I hope it was clear, but I will just go over this again. Circuit switching, what I mean is when you want to move information from point A to point B in a network, what you do is you reserve the entire route, so such that no other users can use that route while you're actively transmitting information. While your protocol is active, you are sending those data frames through a reserved route. And the benefit of that is that your traffic will arrive in order, because probably there's exceptions for everything, but you're mostly guaranteed that your frames will arrive in order, and you can kind of, that's one perk. In the packet switching network, your route is dynamic. You don't reserve any channels for your own purpose. Everyone has kind of a fair use of the network. Maybe there's some prioritization of packets, but we ignore that for now. We assume that everyone has fair access to the network. You're sending these data frames, but you don't know what path ahead of time your frames will take, or your data will take. And you're not guaranteed that those frames will arrive in order. So you have to do a little bit more, to care about, if you need those frames to arrive in order, how do you how do you reshuffle them at the end to make sure? So it's a bit more complicated sometimes to do packet switching, but you get that dynamic routing and fair use. And then with the circuit switching, you get that frames arriving in order, but you kind of lose fair use. Depends on a couple of things, of course. The traffic models, how often are these nodes transmitting? There's some exceptions, of course, but in general, these are the terminologies I've been using. And especially like the pros and cons is a difficult question. It's very dependent on the network. So how could a future quantum network work using packet switching? What we propose is you have this kind of hybrid data frame where you have classical information in front of a quantum payload, and then following the quantum payload is this classical trailer part. I think we've all thought about these things, but we've tried to go in detail with this. And so what would happen is you would put the payload information, or not the packet information, in the header. So where does this data frame have to go? How the other properties we can think of are, how long should this packet live before we drop? We can take a lot of analogies out of the classical regime and use those things that we've been working on for a long time, and kind of integrate them into the quantum setting. So what we call a hybrid frame, and now what you get is you can route this quantum information using dynamic routing. So you don't necessarily need to reserve anything. You're not doing circuit switching. You can potentially do packet switching. Here's a small animation. We just thinking about moving these things all together at the same time. In this setting, we're thinking about moving all these pieces at the same time. That means header and the payload and the trailer move simultaneously. Once they're constructed, they're moving all together. We're sending them at the same time. And the way to do that is you have to use a particular type of multiplexing. So how do you generate this data frame depends on the multiplexing scheme you want to use, or maybe use a combination of these types of multiplexing. So we have the header, the payload, and the trailer. And the way we can do this modulation is multiplexing is either with time, with wave division multiplexing. You can use other degrees of freedom. But in general, we're thinking about time division multiplexing, where you generate this classical signal ahead of the quantum payload. So you send off the classical header, then you start generating the quantum payload, then you send off the trailer, and that moves through the network in synchronous. You can also do wave division multiplexing where they arrive at the same time. One drawback is maybe you spend some time performing some classical processing, and when your quantum payload arrives at the exact same time, then you need to do something with it, maybe store it, maybe you lose some information. So you have to think about, when and where to use these types of multiplexing schemes. So yeah, exactly. So how do we want to generate these things? You have some kind of control unit, and that control unit will trigger a classical transmission with all the payload information, routing information, all these kind of concepts that we have in classical internet. Then we trigger the quantum source, and I don't draw the trailer here, but you would generate the trailer, and all these things will be multiplexed together to generate a frame. And then when this frame arrives at a node, we have some kind of demultiplexing scheme where we firstly might have multiple input signals. So we separate those multiple input signals. Then we need to separate the header from the payload. We can do that over an optical switch. Separate the header, put it into a processor so we know what to do with this data frame. And in the meantime, the quantum payload can either go into a quantum memory or a delay line, something to slow it down for a little bit while we do the classical header processing. Then the header goes on, and we recombine these two pieces together, or three pieces when you draw the trailer, remultiplex them onto a fiber, and then go onward. This is a kind of simplistic approach, but something that potentially we can build already because we're only using optical switches, traditional classical processing, delay lines potentially. So this is something we could build. But if we want to think about the long term, like I'm saying, we might want to think about like a quantum reconfigurable optical add drop multiplexers, or ROADM, that's doing this in bulk and with more automation and with more configurability. And we drew out this diagram of a quantum ROADM where we're doing much more complicated things. And of course, yeah, this is a distant future thing because now we have quantum memories. We have the ability to do error correction with the quantum processor. We could potentially convert the frequency of the payload, or even whatever we need to do. And those technologies don't currently exist in a robust way that we can build this already. But these are things to consider for the future, especially when you're doing kind of a third generation quantum repeater where you're not necessarily using entanglement but more error correction. And then maybe this comes into play when we have that kind of network architecture. So of course these things are not easy to build, so I want to emphasize that there's many challenges to overcome. So because we don't get the ability to do amplification, we in general, I mean, there's some schemes that do exist for amplification, but those are not deterministic, and maybe they're not going to work all the time. So therefore, we have to avoid signal amplification, and this is mainly targeted towards the way we do signal amplification using doped I forget the word the way we do amplification in the classical network. We need to avoid that because it will destroy the quantum signals. So we can't use that. Therefore, we need some kind of other schemes to keep the signal maintained. Also, moving moving these weak signals containing the quantum payload through optical hardware has to be very low loss, because these signals are already quite weak, and we already know that the optical signals cause a lot of loss, and we can't amplify. So therefore, our problem is we need very low loss optical hardware. We need to think about the distance limitations how close can we put our switches? Imagine we can do error correction. Can we put our switches every 10 kilometers, every 2 kilometers, 50 kilometers? There's a lot of consideration there. But I think the general consensus, these things have to be quite close to each other, maybe in the single digit kilometers. And because of that, you might also change your network architecture. Does the classical signal still have to be as strong as it is? We want to avoid these crosstalk effects. For example, the Raman noise between the strong classical signal and the weak quantum signal that are sharing the fiber. But if these switches are only 2 kilometers away, do we still need the same strength of classical signals? So we think about that kind of thing. Maybe the Raman noise is reduced enough that we can still do quantum applications. Maybe we can still, so we think about things like that. And maybe if we want to build a switch that does both classical switching and quantum switching in the same device, do we also have to contain this device in like something, in some kind of fridge? Can we put these in room temperature? Things, what kind of restrictions do we have for building a switch that can support classical and quantum? Yeah. So in terms of networking challenges, of course, storing the quantum states show that there's a quantum memory or delay line, but so this is something to consider. I mean, how good can we store quantum states? We want error correction. This is also very difficult to do right now. We're not able to do this yet, but in the future, people are thinking about using error correction for quantum repeater technology. Do we use quantum relays or do we use quantum repeaters? So relay is kind of a dumb device that doesn't actually do much but forward things on. But quantum repeater design might do something more complicated like error correction. And then the one big thing that we kind of neglect is security of the network. What do we do for security? So that's a kind of something I think is less commonly focused on at the moment. So so this packet switching I was talking about takes the classical header, the quantum payload, and the trailer, and it sends that information through the network all at the same time. And when you do that, when you're processing that header information, like I said, you have to store that quantum payload somewhere. And maybe the technology is not good enough right now to store anything. Maybe too much loss, too much insertion loss from the optical switching, too much, loss. That's always the concern. So what we wanted to do is think about something you can do instead of storing. Maybe you can send the classical header ahead of time to prepare the switch so that when the payload arrives, you don't need to store it. You can just send it right through. And this is not a new concept. This is called burst switching. So we want to make a compromise at the intermediate stage so that we could still do some quantum networking, but we might lose some of that scaling and that kind of pillars that we discussed. And just to show a little animation, what is burst switching? You're sending the header ahead of time so that when the payload arrives, the switching decision has already been made. So that's something we're thinking about for intermediate stage before we go full packet switch. And burst switching, I should mention, also is a bit of a compromise between packet switching and circuit switching, because if you see that animation, you're sending the header over the channel, and you still have to reserve in the time between sending the payload and the header, the channel has to be reserved. Just one channel, not the whole route, but you still have this reservation aspect, and it's a bit less of it's a bit more demanding than packet switching. So you lose you lose quite a bit by doing burst switching, but you gain in that you don't need to store the quantum payload if done correct. Of course, there's challenges involved with that. How much burst time do you need? There's all kinds of challenges that I can explain later in open questions. So what I talk about burst switching is saying you need precise classical quantum transmission scheduling, meaning you need to know precisely, more or less, or else you're using, you need to know precisely you need to know precisely when you send the classical header ahead of time before you send the quantum payload. The precision is important because, as I said, you waste resources when you don't do it right. You're sending this classical control just ahead. You want to do it just in time. You send the header just in time such that this routing decision is made and the quantum payload doesn't have to store in any memory. And if you have robust quantum memories, then what you gain is that burst switching timing doesn't have to be as precise, because if you mess up the timing, then you store the state instead. And if you can do that robustly, then hopefully you don't lose anything. But so the precision is difficult in some sense because you have to accommodate for the number of hops in the route. So as you see, you lose the burst time hop by hop. So this is not a trivial problem to determine the burst switch time, and it might take some more. It definitely will take more research to determine the optimal burst switch aspects for different types of networks, different types of applications. Yeah, so that's something to think about. Also, with the burst switching, we can think about is it can mitigate the crosstalk effect. So if you send the classical signal ahead of time, then later send the quantum payload, then maybe the classical signal is not interfering with the quantum payload as heavily. So that's also an aspect to think about. Maybe we want to do that in any case because we would mitigate crosstalk effect. And I already mentioned, determining this guard time, this burst time is difficult because there's many parameters to consider. So one other design aspect I wanted to mention is a bit futuristic, but why not, is this concept of a hybrid network. And these concepts I've been talking about, this burst switching and this packet switch quantum network, without a quantum repeater, you still are not able to overcome the distance limitations without that quantum repeater. You still are restricted to maybe at best a metropolitan network. So what can we do to kind of get the best of both worlds? Maybe we consider these hybrid networks where we go back to those models I showed before, taking that entanglement-based network, and now we could do internetworking by taking this packet switch network with another packet switch network, and then join them together using this near-term quantum repeater technology, first generation quantum repeater technology, and that we call it a teleportation channel. So what we would gain is in the near distance, maybe we could use packet switching and gain the perks of doing packet switching. And what we can gain is we can have also this distance restriction lifted a little bit. And now we could, how this would work is you would do this packet switching. Let's say this node here, I hope you can see my mouse. No, I've been using the wrong screen. Let's say this node here wants to communicate with a node over here. And what would happen is you would do packet switching up to the egress node here. Then we would teleport those qubits through the teleportation channel, then re-prepare the frame, and then do, again, packet switching until the destination is reached. And now that this node is only doing teleportation at one node, let's say this egress, maybe in the meantime, this channel is just, its only duty is to build up entanglement and teleport. It doesn't have to wait for users to want to use it. It's just always, maybe this is slightly more efficient. That's all open question, right? When is that practical? When is it not practical? Is it possible? These are things. But this hybrid scheme is something to think about. And I think, we're not the only ones to have proposed this. So this is kind of something to think about, like, how do you scale these networks up so that we can, so that we get everything we want. And this is something we're thinking about a little bit. Okay, so now I want to just present a little bit of some simulation results we looked at for, like, can anything run over a packet switched quantum network? Is there too much loss? Is it too difficult? So we took some ideas of some suitable applications, which we think are the ones that are somewhat loss tolerant. That means you can still achieve the application, you can still achieve the protocol goal, even though some of your information is lost in the process. Some of those the key ones that we thought about were QKD, and the distribution of entanglement. So we did a little bit of simulation on these things, and what we found, so we modeled this kind of system where we do BB84, and we are only sending these BB84 states over a line network, meaning you have a network with two nodes at the end, and in between is just a line of switches. There's no yeah, that's what I consider line network. And we've considered this framing of the header with the quantum payload and then the trailer. I don't want to get too far into the secret key rate calculations, but we use a kind of standard formalism, but we've added an additional parameter, which is this K parameter. And the K parameter represents the probability that the node is available to continue the transmission when the payload arrives. So it's a very simple model. We don't think about heavy traffic load. We just want to show, can you route quantum payloads using packet switching? And so what we found is, with the number of hops, of course, you're losing rates. Your rate is diminishing because you're losing every time you enter a node. But what we see is, okay, this is still positive. So in the simplistic model, it could be, everything's optimistic, but of course, it's promising that maybe even with 1 hop, 2 hops, we could get a positive key rate out. And then we went to do entanglement distribution. So what we simulated was the transmission of a BB80, sorry, not BB, this is Bell state here. And the way we did this, we used NetSquid. So NetSquid, with NetSquid, we wanted to focus on how long can we store these Bell pairs such that at the end of the protocol, there's still some entanglement left. So in this simulation, we're really focusing on the memory aspect, and also, how much burst time we could get by with, the minimum burst time we can get by with if we can store quantum payloads. So we assume that we have noisy quantum memories and noisy quantum channels, and we assume that we can store these qubits in memory. And what we measure as a cost function is just the output fidelity. So when the protocol succeeds, what was the fidelity of those qubits in comparison to the perfect state? So we tried 2 different topologies here, where we have the entanglement source in the middle, and we're measuring this fidelity here. And you see, with short distances, even we picked some memory parameters that are maybe optimistic but achievable in the future, and the fidelity could be potentially usable for long distance. Of course, this is still optimistic, I think, but still, promising. At least it's not 0 entirely. We tried the same topology as last time, where you generate the entanglement at one party, send the remainder of the entanglement through the network. Again, we measure the cost. Okay, you lose lots of distance because now the entanglement is generated on one side, but we see that, we see that potentially it's possible. We did an analysis of the burst switching. So we did an analysis against the length of the fiber versus the memory quality. And that's what these plots are showing. So you have fidelity versus the length of the fibers per hop. Oh no, sorry, total distance that the entanglement is traveling, and duration, and the T1, T2 time of the quantum memory. So it seems like in the millisecond regime is where things start to become a bit positive. So we would need potentially millisecond storage for doing this protocol. And then we're looking at the burst time, the duration of the burst. Sorry. This is the duration of the time the packet stays at the node per hop. So this is the processing time in nanoseconds. And this is, again, a comparison with the memory. And again, you see like milliseconds, even when the processing time is small, we still need to be able to store the payloads for quite long. Okay. How much time is it? Okay, so I just quickly go over these open problems, and we should have 10 minutes for questions. So yeah, the things that we focus on the most is, of course, the crosstalk. How do we design the network and the protocols to coexist with data transmission to minimize these crosstalk effects? Especially with the focus on the Raman noise. The analysis we are focusing on now is, in what scenarios would packet switching outperform other network designs? What metrics do we consider that, to measure those performance improvements? How do we generate the frames efficiently? How do we choose that guard time for the burst switching? Can we reduce the header processing time in the quantum network? We've seen some results that it takes about 200 microseconds in some cases. Can we make that half as much? Do we need as much data? Can we simplify the protocols? What do we include in the frame header? What's important for quantum message transmission? And many more problems. This is, of course, a future vision. So there's many problems to consider. And the kind of vision I want to summarize with is, if we expect quantum networks to be widely used, then we better start thinking about user scalability and other scalability aspects now, because we might take a direction too far and find out that we lost something along the way. And this idea of the hybrid approach, where we're taking different types of network architectures, mixing them together, so that we could get a bit of the benefits of each, is something I think that could be important. And I wanted to point out one other aspect that kind of does a great job of presenting future outlooks for quantum networks is this paper. This is called Designing Tomorrow's Quantum Internet. I think this is a very good read. It's also promoting this kind of idea that we have to move away from circuit switching, because history has taught us we do better with packet switching. It depends on some aspects, of course. There's, of course, parts of networks that are still circuit switched today because it's better. So it's always about consideration. But I think keeping things in mind for designing the quantum internet is important to think about now. So that's the end of the talk. And in conclusion, I wanted to just say these last 4 points: that packet switching in quantum networks could be a viable means for scaling quantum networks up. Burst switching can be this kind of intermediate stage thing where we do in order to be able to implement some quantum network applications. Packet switching in quantum networks could also lead to better network utilization that we saw in the past. And in the intermediate future, we could think about these hybrid networks. So yeah, thanks everyone for the attention. I write my contact information here, and this is the archive ID of the paper. So if you want to get in touch for further discussion, feel free to reach out.
All right. Thanks, Stephen. Wojtek, you want to run the Q&A or shall I?
No. I was actually going to ask you, can you run it, and I'll make notes of the Q&A.
Okay, good. Let's see. So there've been several questions or comments here in the chat. I think most of them were actually answered pretty well by Wojtek. A bunch of them were from Scott. Scott, do you want to ask anything in that you're still unclear about, or you want to bring up with Stephen instead of me and Wojtek?
No, I think I'm good.
Okay. Anyone else questions you want to bring up in via voice, or you can add new comments into the chat. Yeah, we have one from Jessica. Jessica, do you just want me to read it, or do you want to speak up?
Can you hear me?
Yeah, sure.
Yep.
So
my
Jessica
question
has.
is, yes.
Sorry, say that again.
It's the one in the chat.
Okay. So, Stephen, question from Jessica in the chat. Are the classical headers separated from the quantum payload? If yes, how does the coupling between the header and the payload take place? How do you manage a payload or a classical header loss? Now, that's a good question.
So in our scheme, we consider 2 different ways to separate. Well, I mean, they're separated and depends on the multiplexing scheme. So we separated using time, and we separated using wavelength. So they're not, for example, using the same quantum signal. We're not using qubits to represent the classical header. We want to do the classical header in the traditional way. So I guess the answer to that part is yes. If yes, how does the coupling between the header and payload take place? So there we consider some multiplexing scheme. But this is kind of a general thing right now. We want to investigate this further, because it's, we didn't build it yet. We don't know what's the best way to do it. But the coupling is with some kind of either optical switching or multiplexing scheme, where we can couple these things onto the same fiber. I think that's, if I understood correctly, that was the question. And how do you manage payload or classical header loss? So this is I would say, application depend. I think I'm just skimming. I didn't notice the chat during the talk, but what we do for loss depends on what the protocol is. If the header is lost, then not much you can do because the quantum payload itself has no information about itself. It has to be dropped. But if you drop the payload and you have the header, and then you can somehow observe that the payload was lost, you might ask for a retransmission if the application allows for it. For example, when you use a QKD, the information itself is represented in a quantum way, but in a sense, it's just classical information. You could regenerate it, and there's no problem. With entanglement, it's the same. You lose entanglement, it's not like you lost an important aspect of information. But if it's something like quantum computing, when you take time to prepare the quantum state, then you transmit the quantum state and it's lost, you can't just say retransmit that quantum state. You have to run the algorithm again, potentially. We don't know. So that's something also an aspect to consider. But of course, it depends. We have an idea of what it depends on.
Good. Patrick also has a good question there, just above Jessica's. Isn't QEC, that would be quantum error correction, a challenge for your approach? Indeed, it's necessary to transmit on the same virtual circuit the qubit with its redundant qubits to apply the error correction. So
Yeah,
an
yeah. I
encoded
think
state
so.
would certainly mean that you're encoding some logical qubit on a set of photons, and presumably all those photons would travel together.
Exactly. So that quantum payload we tried to keep arbitrary. You could generate some kind of graph state, do your error correction scheme, transmit the whole state over, perform the error correction scheme, and then forward on. This is something that's this is, I think, is independent of the protocol, because if we want to do just direct transmission without packet switching with just third generation quantum repeater, the same challenge would apply.
We actually wrote a paper on those loss probabilities and what are necessary some years ago, which we actually haven't gotten officially published yet in peer-reviewed journal. I'll put the link in the chat. Other questions? How are we doing on time? It's 52 after, so we've still got plenty of time. Comment from Roland. It seems you implicitly consider hop-by-hop routing decisions for packet switching. However, other schemes may be possible, e.g. source routing or label switching. Do you consider the latter out of scope? That's actually an interesting question. There are multiple ways to achieve this kind of multiplexing, right?
Yeah, I think this idea of the packet switch, just to keep it like, I mean, we don't want to restrict anything right now. So let me see. No, like out of scope is, what's out of scope for quantum networks? I don't know. It's hard to say. So, but I think any type of scheme that is taking some dynamic routing approach or some kind of packets approach is something feasible that we want. Basically, we want that scaling. However it's achieved is the way we go, right? So there's something to consider. Right? I don't know. Yeah, I would say no, not out of scope.
Good. Other questions? Have I missed anything that didn't get covered from back in the chat? Anybody have anything else? You can stick your hand up, or you don't have to do it in the chat. You can stick your hand up here and we can let anyone speak up. While other people, well, let's see, we have one here. Oh, okay. Just thanks from Patrick. I actually have two comments, I guess. I'm going to be the guy who says, I have a comment, not a question, right? 2 weeks ago, we were at the workshop for quantum repeaters and networks in Chicago, and Farzam was there. Farzam, what's Farzam's last name? I'm blanking on his last name. He works for Siena, which makes optical components. And he's been working on their approach to quantum stuff. And he's adamant that The quantum channel is going to have to be run at 1310 nanometers with all of the classical traffic up around 1550. Otherwise, you're not going to get you're not going to get enough extinction of the classical channel, even with fairly narrow filters on it, even with good optical multiplexing and demultiplexing. Have you all looked at that at Cisco?
Not yet, no.
I know there has been some work on multiplexing QKD with classical traffic into the same fiber, but I don't remember off the top of my head who did it, and I don't remember what wavelengths they were working at.
Yeah, one observation we made, like, this vision for being so far in the future doesn't restrict us from using technology that's kind of available today, but maybe not far developed. So we're, like, for example, I'm being specific about hollow core fiber, and probably some of us have seen these experiments where they're transmitting classical signals at full strength and doing QKD at the same time. So maybe, what if the quantum network, what if the entire internet was built off hollow core fiber? Can we then consider this? So these things are just kind of open. I mean, these are just preliminary ideas. I mean, all these directions need to be explored more in depth. So this idea that what bandwidth we want to use for the transmission, we don't know yet. Something we need to put up a lab and experiment.
I've been pushing for well, not like in a serious level, but I've been pushing people over here to think about hollow core fiber for years. They'll go to tremendous effort to cut 10 milliseconds off of the latency between Tokyo and London when they could cut 40 or 50 off of it by going to hollow core fiber. But the hollow core fiber still has loss that's measured in dB per meter, not fractions of a dB per kilometer. It's still measured in dB per meter, right?
So yeah, I mean, but it had the nice property was you can mix the states and basically negligible crosstalk. But like that's I guess a kind of a younger thing, right? So we'll see how that progresses. Maybe that comes into play. Could be quite important for these kind of technology for future quantum networks. Nice.
Bruno says the experimental work that was done was actually done using Cisco multiplexers. How nice.
Oh, this one. Yeah, this one. Okay, there's two papers at least that I know. This one and one more that I was using. I don't know if they had any. Yeah, I have to see how they did theirs again, but.
Bruno, does the paper say, or do you know easily what the wavelengths were for the classical and the quantum channels in those experiments? Does it say someplace readily accessible? He's looking, he says. All right, I actually have, putting just on my personal hat, nothing to do with QIRG chairing. I actually have a request. My research group has created a set of icons for node types for quantum networks, and we would love to have Cisco adopt them. I've been talking to people from other research groups, both in the U.S. and Europe, and we've gotten some who've said that they'll use them, and I think it would be a big win if we all sort of standardized on one set of icons. It'll make it a lot easier to share information.
Yeah, if you send me the link, I'll start using them.
Bruno says, in fact, it was the wavelengths I just said, which would be 1310 for the quantum and 1550 for the classical.
But this is over hollow core or just standard fiber?
I'm sure that's over standard fiber.
Okay.
Standard single core fiber, I presume.
Okay, the result I was mentioning was a hollow core result. This was about half a year ago, I think.
All right, it's 1 minute to the top of the hour, and people are already starting to drop off. I'm sure a lot of people have their next meetings or whatever. Stephen, we should all thank you for this presentation. I thought it was really fantastic. I learned quite a bit about what you guys are doing and the way you're thinking about it. Wojtek, any other final comments?
No, thanks a lot, Stephen. That's about it. We'll try to keep up with these seminars. I think 2 times a year seems about the right frequency. So we'll keep you all posted on the mailing list. If any of you have any more questions or discussions, please just continue on the mailing list. We're all on there, and so is Stephen, and so are all of you, hopefully. So you can always just continue there.
All right. Thanks a lot.
And I'm looking forward to seeing all of you all in Tokyo in March. Colin, any IRTF business or anything you want to say, and you want to stick anything in before we hang up? Put Colin on the spot real quick.
Not sure he's tuned in.
He's not responding, so I presume that means no.
Yeah. So yeah, with that, let's wrap it up. And yeah, thanks everybody. Thanks, Stephen.
Thank you.
Thanks, Stephen.
All right.
Thank you all.
See you then.
Bye.
Bye-bye.